We ended our previous lecture with theorem 5.3, which was about a system, okay, in this form. U is the input and Y is our output. And we suppose that the system satisfies the following properties. First of all, its input to state is stable, okay, and also the function that's used to describe the output. The norm of that function can always be bounded by the norm of x passed through some class k function plus the norm of u passed through some other class k function plus some constant eta. Okay. And this inequality was uniform in the sense that these class k functions, they were independent of x and u, so this is true for all x and u. So if this pair of conditions are satisfied, and the theorem claimed that system has to be L-infinity stable, okay? Meaning that the L-infinity norm of the output can always be upper bounded by the L-infinity norm of the input passed through some class k function, comma, and plus some constant that we denote by beta. Okay, so we begin today this lecture by an example where this tool is exercised. Consider the following second-order system. x1 dot equals minus x1 cubed plus x2. x2 dot equals minus x1 minus x2 cubed plus u. Okay, and for the system, the output, suppose, is x1 plus x2. And we want to study, suppose, the effect of the input on the output. Okay, so we want to study the system from the input-output relationship point of view, and for that, the tool that we have is the L stability. Okay. Now, what we're going to do now is we're going to show first that the system is input to state stable, and then it's easy to show that the second condition also holds, and together, thanks to theorem 5.3, we're going to establish that the system has to be L-infinity stable. Okay, so how we establish input to state stability? We're going to establish input to state stability by the help of a Lyapunov function. And for that, our candidate is the most standard candidate ever, okay? The norm square of the state, x1 squared plus x2 squared. So let's figure out what happens to the derivative of this function along the solutions of this system. So what we do is we compute v dot, okay, v dot of x equals x1 times x1 dot plus x2 times x2 dot. x1 dot is here, x2 dot is here, so therefore what we have is minus 2x1 to the 4 plus 2x1 x2. So this is x1 times x1 dot. Okay. What else? And we also have to add to this 2 times x2 times x2 dot, and that yields minus 2x1 x2 minus 2x2 to the 4 plus 2x2 u. Okay. Now this term and this term, they cancel out, and this we can write as minus x1 to the 4 plus 2x1 squared x2 squared plus x2 to the 4 minus x1 to the 4 minus 2x1 squared x2 squared plus x2 to the 4. Okay. So if you add those two terms, we have x1 to the 4 here, x1 to the 4 here, with minus signs in front, and that together makes minus 2x1 to the 4, and the same for x2 to the 4. And here we have a cross term, and here the same cross term, but with the opposite sign, therefore they also cancel out one another, and what we're left with, this sum is simply minus 2x1 to the 4 minus 2x2 to the 4. Okay, and plus we have 2x2u. And why have we written this simple sum minus 2x1 to the 4 minus 2x to the 4 in this long form? It's because this whole thing can be written as minus x1 squared plus x2 squared. Then you take the square. Okay, this can be written as this. Likewise, this can be written as minus x1 squared minus x2 squared plus we have 2x2u. Okay, now working with the Euclidean norm, x1 squared plus x2 squared is norm square, and then you take square of the norm squares, so that makes norm raised to the power 4. So what we have is minus norm of x raised to the power 4 for this term. Now this term, okay, it's something square, therefore it's never negative, but it has a minus sign in front, therefore this whole thing is never positive. Therefore we can just ignore it, and still that will be an upper bound on v that of x. So we can remove that term and replace this equality with less than or equal to sign and write 2x2 times u. Now this can be written as 2 times absolute value of x2 times absolute value of u, and absolute value of x2 is never larger than the norm of x. Therefore, this we can write as norm of x times norm of u. Well, by norm of u we simply mean the absolute value of u because u is a scalar here. Okay, and finally, that can be written as 1/2 x raised to the 4. Then you take the other half to bound effect of the input on the state, by which I mean following 1/2 norm of x times norm of x cubed minus 4 times the norm of u. Okay. This sum of terms equals the what appears in the line above. Okay. Now the question is, why have you written this as this expression? Because we know that from one of our earlier theorems, if we have a positive definite function and its derivative is negative definite or negative, provided that norm of the state is larger in some sense, the norm of the input, then your system is input to state stable. Okay, and this is exactly what we have here. Okay, if norm of x is larger than norm of u in the sense that norm of x cubed is larger than 4 times the norm of u, then this is positive, but if we have a minus sign in front, therefore this whole thing is negative, therefore we can ignore it, and beta is less than or equal to minus 1/2 norm of x raised to the power 4. Okay, and that by an earlier theorem yields equal to state stability. So to sum up, we have v dot of x is negative, okay, minus 1/2 times norm of x raised to the power 4, and since v of x was norm of x squared, we have v dot of x less than or equal to that. When norm of x is greater than or equal to 4 1/3, then you take the cube root of the norm of input. And from an earlier theorem, we know that system has to be ISS. Okay, so therefore for this system we have established the first condition of the theorem 5.3. Second condition was that the function that describes the output, in this case it's x1 plus x2, we want to be able to bound that by norm of x passed through some class K function plus norm of u passed through some other class K function. And in this case, it's especially straightforward to establish that condition, h of xu. Okay, and h in our example simply is x1 plus x2. That can be written as x1. That can be upper bounded by one norm of the state, and one norm of the state is, or can be upper bounded by square root of 2 times the 2 norm of the state, and by that we have the second condition also satisfied. Okay. Finally, by the previous theorem 5.3, the system is L infinity state. Okay, so it's bounded input, bounded output system in the L infinity sense. Okay. The next thing that we're going to consider is a very useful lemma, okay, a result that we will use for L2 stability. Consider the system. Okay. Our standard workbench, okay, for L stability, where F is locally Lipschitz and H is a continuous function of both the state and the input. Okay. And suppose that for this system we have function b, which is positive, semi-indefinite. Okay, and Rn is the space where the state resides. Okay. So it's an nth order system function such that its derivative, or put in other words, its gradient of that function with the or the inner product of the gradient of that function with the right hand side of our system, which is no other than the time derivative of this function v along the solutions of the system, can always be upper bounded by a, then we have gamma squared norm of u squared minus norm of y squared. Okay, where a and gamma are positive constants. Okay, suppose that we have a v, positive semi-indefinite. Okay, that is for all values of x, it's never negative. Okay, sometimes positive, sometimes 0. Then the system is finite gain L2 stable with L2 gain no larger than gamma, and gamma is what appears here. Not larger than, okay. In particular, we can write the L2 norm of the output is always less than equal to gamma times the alpha norm of the input plus the term that's determined by the initial conditions through this expression v of the initial state divided by a, and then you take the square root. Now let's demonstrate this claim. Okay, let's provide a proof for that. We're going to use it a couple of times. It's very useful result. We're going to call it the lemma. Okay. So here goes proof. What we have here is v dot. Okay, the time derivative of our function v along the solutions of the system x that equals f of xu, and that's upper bounded by this difference of squares of the norms of the input and the output at a particular time. And so that's what we start with, v dot less than or equal to a times gamma squared u minus y squared. And this is true for all particular times, okay, t. So what we do is we integrate both sides from 0 to t. And if you do that, you have vx of t minus vx of 0. Okay, so that's the integral of this term v dot from t equals 0 to t. And that's less than or equal to a gamma squared from 0 to t, and then we're integrating the norm square of the input d tau minus, we do the same thing to the output y tau squared d tau. Okay, so we started with this condition here, which we assume holds. Then we integrated both sides of the inequality. So, and let's call this inequality 1. Now, let's write this 0 to t y tau squared d tau. Okay. So let's concentrate on that term. So that term is 0 t y tau d tau. Okay. So we simply rewrote the same thing. Okay, clearly, since both are equal, this thing is less than equal to itself. Plus, we can add a non-negative term to it, and our non-negative term that we want to add is v of x of t. Okay? We can do that without hurting this inequality, because we told that v is a positive semi-definite function. Therefore, it's never negative. Hence, we can add it to the right-hand side of the inequality. Now, if you do that, we realize the following. Take this term, okay, and throw it to the other side, and what we have is vx of t plus this, okay, what we have here. And then take this guy, throw it to the other side, and you have this integral of the input plus the initial value of the Lyapunov function, okay, v. Hence, using 1, this is less than equal to a gamma squared, and then integral u tau squared d tau plus v of x of 0. And from this line to the next, we use simply what we obtained by integrating the assumed condition. Therefore, dividing both sides by a, and that won't change the direction of inequality because a is a positive number. We have 0 to t y tau squared d tau is less than or equal to gamma squared 0 to t u tau squared d tau plus v of x of 0 scaled by a. And then this implies the same thing, but with square roots. Theta 1/2 less than gamma 0 to t. U of tau squared d tau square root plus v of x 0 over a square root. Okay. Again, if you take the square of both sides, what you have is this inequality plus you have the positive cross term, and then you can always, since the cross term is positive, it's clear that this implies that. And we have therefore no other than, we have reached therefore no other than the definition of L2 stability. Okay, the L2 norm of the output is represented by L2 norm of the input times a constant, okay, plus some constant that is determined by the initial condition. Okay, therefore, the system is L2 finite gain, L2 stable with gain gamma, okay, or something smaller perhaps. Hence, is less than equal to gamma times the L2 norm of input plus V of x of 0 over A. And that completes the proof. Okay. Now, using this lemma, let's now study a linear circuit from the input-output point of view. So let's consider the standard series RLC circuit. RLC circuit. And this circuit is driven by this voltage source, and the voltage provided by independent voltage source is what we're calling U. So that's our input to our system. Resistance, inductance, and this is the capacitance. Let us choose our states as this is a second order system. Let us choose as our first state the current of the inductor, which by the way is the current of everything because everything is in series connection. And let's choose the second set variable as the voltage of the capacitor, x1 and x2. And also let's choose the output as the current that flows in the circuit. Clearly this output is no other than our first state variable, x1. So let's obtain the system, the model of the system. So what we have is L x1 dot is the potential difference of the inductor. Okay, V of L, voltage of the inductor, and V of L by KL can be written as a linear combination of these three voltages. Okay, the voltage of the resistor, the voltage of the capacitor, and the input voltage. What we have is U minus R times the resistor current, which is no other than x1, and finally minus the capacitor voltage. Okay, and how about the other state equation? Cx2 dot. Okay, this is the capacitor current by the terminal equation of the capacitor, and capacitor current by KCl, same as the inductor current. Okay. And that's our state equation. Let's put it in more organized form. So x dot, and x is x1, x2, our state, and state variables are defined here, x1 and x2. So x dot equals the A matrix times x plus the B matrix times U. and the output equals C matrix times X plus the D matrix times, in this case, the D matrix is 0. We don't have to write it. So what's A matrix, what's B matrix, and what's C matrix? Let's figure out the entries of A and B matrices. For that, we look at the equations. So what's x1 dot? X1 dot is minus R over L x1, okay, minus 1 over L x2, okay, plus 1 over L u. Okay, so those are the entries of the first rows. And how about the x2 dot? X2 dot is simply 1 over C x1 plus 0 times x2 plus 0 times u. Okay, so those are A and B matrices. As for the C matrix, Y is the current that flows over everything, and Y simply by KCL equals x1. Therefore, we have x1, 1 times x1 plus 0 times x2 is our output. Now, let's analyze the input-output behavior, and for that we're going to use a positive function. And whenever you have a physical system, usually the function to work with is the energy function. It doesn't always work, but usually it works, or even if it doesn't work, it gives you something, some meaningful information. So let's write down the total stored energy in this circuit. We have two energy storing elements, the inductor and the capacitor. And let's write down the energy, therefore, as the stored energy in the inductor plus the stored energy in the capacitor. Stored energy in the inductor equals 1/2 times the inductance times the square of the current passing through the inductor at that particular time. So what we have is 1/2 L x1 squared. That's the stored energy in the inductor. For the capacitor, we have the dual case 1/2 C times, this time we square the voltage. Okay, and this sum together, what we're calling the total stored energy in the circuit at any given time. Now that this is a quadratic function, and it can be written as x transpose times a symmetric positive definite matrix times x. Okay. Usually we call this matrix P. In this case, our P is L over 2, 0, 0, and here we have C over 2. It's a diagonal matrix. Okay. Now, by conservation of power, which can be established through Telegrand's theorem, what we have to have is that the power supplied by the input source must be equal the sum of powers associated to the remaining components, the resistor, inductor, and the capacitor. So that means the power supplied by the source must equal power consumed by resistor, PR, plus the powers associated to inductor and the capacitors, PL and PC. The power of the resistor is R times the current square, or simply the current times voltage. And therefore, this is R times Y squared. Okay. The power supplied by the source is the voltage of the source times the current leaving the source. Therefore, this is U times Y. And PL plus PC together, those sum of those two powers must be the rate of change of the energy. Okay, because power by definition is rate of change of energy. So here we have V dot. Okay. Therefore, what we have obtained is Uy equals R Y squared plus V dot, where V is the total stored energy in the circuit. Okay, let's call this one. Here is a claim which we will use. Which we will prove using the previous lemma. Claim is the following. this equation, okay, that relates the power of the resistor, the rate of change of the total stored energy, and the power supplied by the source implies that this system is L2 stable with L2 gain 1 over R, okay, over the conductance of the resistor. Okay, so let's establish this claim. Now, claim is true because we can write V dot Uy minus Ry squared. Okay, so this is what we have obtained, and now we're going to transform this expression to the expression that appeared in the previous lemma. This can be written as minus 2 over R U minus Ry squared plus 1 over 2R U squared minus R over 2 Y squared. Okay. If you open this term and add everything up, there will be some cancellations, and you will be left with this Uy minus Ry squared. Okay. And then this is less than or equal to, this is square of something. Okay, therefore it's never negative, and here there is a minus sign in front, therefore this thing is never positive. We can just ignore it and replace this equality with inequality less than or equal to sign, and write V dot less than or equal to this, something U squared minus something else Y squared. And that difference can be written as R over 2 1 over R squared U squared minus Y squared. Okay, so V dot, where V is a positive function, less than or equal to something times U squared minus Y squared. So let's therefore list what we have. This is what we have. Okay, just obtain minus Y squared plus we have the previous lemma. Now that is now in the form that appeared in the previous lemma. Therefore, the system is L2 stable. In fact, finite gain L2 stable, and L2 gain is 1 over R. Now this observation can be generalized in a very straightforward manner to following lemma. Lemma 6.5 for the text. If the following system x dot equals f of xu y equals h xu, where f and h satisfy the usual assumptions, x in R n and u y in R n. Note that we're making a very specific condition, assumption on the dimension of input and output. Namely, we assume that the dimensions of the input vector or the size of the input vector and output vector, they are the same, so that inner product of those two signals is well defined. Okay. Input and output are of the same size. to be output strictly passive. Okay. And we're going to revisit this and some more general concepts when we start studying passivity. Okay. With U transpose Y, always upper bounds, this term B dot plus delta Y transpose Y, where delta is a positive constant and function V is positive semi-definite, and we're going to call that function storage function when we study passivity. Is positive semi-definite. Okay, then the system is finitely L2 stable with L2 gain equals 1 over delta or smaller. Okay. And demonstration of that lemma 6.5 is just the same as what we did in the example with the circuit example. Okay, the RLC circuit. Okay, now let's apply this lemma to the following example. Consider the system x1 dot equals x2 dot equals minus a x1 cube minus k x2 plus u. And for this system, output is the second state variable y equals x2. And the parameters a and k are positive constants. So let's work with the following positive definite function. V of x equals a over 4 x1 raised to the power of 4 plus 1 half x2 squared. Okay, so clearly it's positive semi-definite because it's positive definite. Then what's v dot? V dot is a x1 cubed times x1 dot plus x2 times x2 dot. The dots are here, x1 dot and x2 dot. And if you write them down, this is what you have: a x1 cubed x2 minus a x2 x1 cubed minus k x2 squared plus x2 times u, or in other words, y times u, because the output was the second state variable. Okay, so this and that cancel. What we have is minus k x2 squared minus x2u, and that's minus k y squared minus the product of the output and the input. Okay. So therefore we have uy equals v dot plus ky squared. Then using lemma 6.5 we have the system is L2 stable with gain no larger than 1 over k. The system is L2 stable finite gain L2 stable with L2 gain no larger than 1 over k, where k appears here. Okay. Now, we're going to end this lecture with an example from the LTI domain. Okay. We're going to consider a linear time invariant system and we'll try to figure out the relation between the Riccati equation and L2 stability. LTI system. X dot equals AX plus BU and Y equals CX. Suppose there exists a symmetric positive definite matrix, which we're calling P, satisfying the celebrated Riccati equation from the quadratic regulator optimum control. ATP plus PA plus 1 over gamma square PE E transpose P plus C transpose C equals 0. Okay. For some gamma positive, then the system is finite gain L2 stable with L2 gain less than or equal to gamma. Okay. Now let's establish a claim we're going to use the lemma. Now what we're going to do is we're going to use the Lyapunov function, of course, a semi-definite function. In this case, it's very positive. We're going to construct that function using P. Okay. So let V of x be x transpose Px is a positive definite function of the state, okay, because P is symmetric positive definite matrix. Let's compute V dot. Then V dot of x equals x transpose times Px dot plus x dot transpose times Px. And x dot and also x dot transpose is here. It's Ax plus Bu and x plus Bu transpose. If you do that, this is what you have. X transpose PA x plus x transpose A transpose Px plus 2x transpose P Bu. Okay. Now this is scalar. Okay, x transpose PAX. Therefore, it equals its transpose, and if you take the transpose of it, you obtain this. So we could have written this whole thing as 2 times x transpose ATPX plus 2 times x transpose PBU. But for reasons of convention, because the Riccati equation given in this form, because we want to be able to use the Riccati equation, we write it in this form. Okay. What else? This term can be we express as follows: 2x transpose p bu equals minus gamma square norm of u 1 over gamma square b transpose p x norm square. And by norm we mean Euclidean norm. Okay? And the norm square, therefore, is this thing transpose times itself. So that's what we mean. Plus gamma square u transpose u plus 1 over gamma square x transpose p b b transpose px. Okay. And then if you just write those norm squares as this thing transposed by itself and figure out the cancellations. There's a lot of cancellations, and you'll be left with this term 2x transpose PBU. Okay? But this simple term we write in this a little bit complicated fashion because we want to use previous results that we established. Okay? And also we want to use the Riccati equation. So therefore we can write v dot of x equals x transpose ATP plus PA plus 1 over gamma square PB B transpose PX. Okay, this is v dot of x. We take these two terms and they generate this sum of matrices, and then from rewriting this expression we will have a term like that, and that term appears here. And what remains is the following: plus gamma square norm of u square minus gamma square u minus 1 over gamma square E transpose P x norm square. Okay. And now, by Riccati equation, we know that this thing here equals minus C transpose. It's minus C transpose. So what we have, therefore, is minus Cx transpose times Cx. And Cx is no other than the output. Therefore, this term here is minus norm square of the output. Okay, this is less than or equal to minus x transpose C transpose Cx plus gamma square times norm square of the input. And we simply discarded this term because it's never positive, and the inequality is replaced then by this inequality. Okay. Once again, this, since C of x is y, here we have gamma square norm of u square minus norm of y square. Okay. And then the result holds y to that. That we have seen a few minutes